For 15 years, Denisovans were a ghost species, known from a finger bone, a handful of teeth, and the DNA they left inside billions of living people. No skull, no face. Meanwhile, a massive cranium, hidden in a well since 1933, sat in a Chinese museum without an identity. In June 2025, two landmark studies finally connected them. And the answer, I think, forces a fundamental rethink of our own origins. Denisovans first appeared in the scientific record in 2010, not as a skeleton or a skull, but as a sliver of bone, one-finger phalanx unearthed deep inside Denisova Cave in the Altai Mountains. Geneticists sequenced its mitochondrial DNA and found something astonishing, a branch of the human family tree that was neither Neanderthal nor modern human. Yet, for the next decade and a half, this entire species existed almost entirely on paper and in code. Every fossil since, an oversized molar from the same cave, a jaw from the high Tibetan plateau, a rib, a tooth from Cobra Cave, was fragmentary, isolated, and silent about the face or form of the Denisovan people. What strikes me is how much of their story was told not by bones, but by genes scattered through living people. Today, 4 to 6% of the ancestry of Papuans, Aboriginal Australians, and Melanesians traces back to Denisovans. In Tibetans, a single gene, EPS1, lets them thrive at high altitude, a gift from a population that vanished tens of thousands of years ago. For scientists, this was both thrilling and deeply frustrating. We could read Denisovan DNA in the genomes of millions of people, but had no idea what they looked like. Artists tried to reconstruct their faces using epigenetic clues from that original finger bone, but it always felt like guesswork, a shadow projected onto a wall. To me, this feels like a paradox, a species so genetically present, yet visually invisible. Every time a new fragment turned up, the hope was the same. Maybe this one would finally reveal a face. The longing for a skull, for something to anchor all that genetic data, became almost an obsession in the field. Any complete cranium, if it ever appeared, would change everything. In 1933, as workers dug the foundations for the Dongjiang Bridge over the Songhua River in Harbin, one of them unearthed a skull unlike any he had seen before, massive, mineralized, unmistakably ancient. With Japanese occupation tightening its grip on Manchuria, the laborer made a decision that feels both desperate and oddly hopeful. He lowered the skull into an abandoned well, hiding it from soldiers who were known to seize anything of value. The act itself is shrouded in family memory, not official record. There are no police logs or municipal files confirming the discovery, only the testimony of the workers' descendants, passed down like a secret. For decades, the skull's existence flickered through rumor and private recollection. The family's story describes a wax-sealed box kept in a storeroom, never shown to outsiders. No photographs, no newspaper clippings, just the weight of a relic hidden through war, revolution, and the shifting tides of Chinese history. The chain of custody, at least before 2018, is a black hole in the archival record. That gap, I think, is part of what makes this specimen feel so human. Its journey marked by fear, secrecy, and the urge to protect something precious, even as the world outside changed beyond recognition. The story takes a turn in the spring of 2018. On March 12, 2018, the family handed the skull over to the Geoscience Museum at Hebei Geo University. It received accession number HBSM 2018-000018A, along with a donation form and a brief provenance statement that repeated the tale of wartime concealment. Chiang Ji, the museum's lead paleoanthropologist, became its custodian, but Ji has never fully embraced the family's version of events. He has voiced skepticism about the timeline and the lack of documentation, warning that legends can grow in the shadows of missing evidence. To me, this tension between oral tradition and scientific rigor sits at the heart of the Dragon Man story. It is a reminder that every great fossil carries not just the marks of deep time, but the fingerprints of the people who found, hid, and finally revealed it. The Harbin skull arrived in scientific hands as a riddle. Its naso-occipital length, 213 millimeters, set a record among archaic humans. The cranial capacity, about 1,420 cubic centimeters, overlapped with both Neanderthals and modern humans. But the details refused easy classification. A single continuous brow ridge dominated the face, thick and unbroken, unlike anything seen in living people. The face itself was broad and flat, the orbits nearly square, the vault low and elongated. Even the lone surviving molar was oversized, hinting at a jaw built for power. Uranium-thorium dating placed the fossil at least 146,000 years old, deep in the late Middle Pleistocene. Shijun Ni and his team spent months measuring and comparing. Their analysis, published in June 2021, argued the Harbin skull did not fit within Homo sapiens or Neanderthal boundaries. They named it Homo longi, Dragon River Man, and suggested it might be our closest extinct relative. Their statistical approach was precise. A multivariate analysis of variance comparing 25 cranial features placed Harbin outside the 95% confidence intervals for both Neanderthals and modern humans. Anatomy alone, they argued, justified a new species. But the claim met immediate skepticism. Some pointed to Denisovans, a mysterious population known mostly from DNA and a few teeth, as a better fit for Harbin's blend of features. Without nuclear DNA from the skull, the debate stalled. Even Chiang Ji, who brought the fossil to light, admitted the limits of anatomy and the uncertainty of its origins. The field found itself at an impasse, waiting for molecular evidence to settle what bones alone could not. Population genetics has given us a timeline for Denisovan divergence, roughly 400,000 years since they split from Neanderthals, and about 600,000 from modern humans. These numbers come from painstaking modeling of ancient genomes, tracking the slow drift of alleles over thousands of generations. The evidence for Denisovan ancestry in living people is robust. Papuans, Aboriginal Australians, Melanesians, and even some Southeast Asian groups carry between 4 and 8% Denisovan DNA. In Tibetans, a single gene introgressed from Denisovans, EPAS1, stands out as a textbook case of adaptive evolution. But the way I see it, these models, impressive as they are, have always felt like a map drawn from shadows. For years, researchers tried to predict Denisovan anatomy by reading the chemical scars left on ancient DNA. In 2019, a team used methylation patterns from the original Denisova finger bone to reconstruct a hypothetical face. Broad, robust, with a projecting midface and heavy jaw. That portrait, rendered as a bust, became the public image of Denisovans. Yet even the authors admitted that methylation to morphology predictions explain only a fraction of facial variation. Post-mortem changes, incomplete reference data, and the sheer distance between gene regulation and bone shape make these reconstructions educated guesses at best. No new Denisovan individuals surfaced to test these predictions. The few fossils, teeth, jaw fragments, a rib, offered no full face and certainly no cranium. Each new fragment extended the range of Denisovan DNA, but never their visible form. The scientific community, in my opinion, was left modeling ghosts, visible in genetic code, but invisible in the fossil record. That's why, for all the excitement around population genetic dating and epigenetic modeling, the field still waited for a laboratory breakthrough, something that could finally anchor these predictions in hard evidence. June 18th, 2025 marked a turning point. 2 landmark studies published in Cell and Science finally resolved the identity of the Harbin skull. Xiaomei Fu's team at the Institute of Vertebrate Paleontology and Paleoanthropology bypassed failed nuclear DNA attempts by targeting the dental calculus and petrous bone. In the calculus, they sequenced a near-complete mitochondrial genome at 0.4 times coverage, uncovering 27 variants unique to Denisovans. The DNA damage, short fragments and C to T substitutions, spoke of ancient origins and not modern contamination. These were the molecular scars of deep time. The proteomics team extracted 95 proteins and over 20,000 peptides from just 200 milligrams of petrous bone. 3 peptide markers, each in KOL1A2, KOL18A1, and KOL26A1, matched Denisovans' specific amino acid changes identical to those found in the Altai Denisovan. Every step was rigorously controlled. Extraction blanks, UDG treatment, and independent labs confirmed the findings. Modern DNA contamination was measured at less than 0.02%, with no Denisovan signals in any blank. Sijun Ni, who led the original anatomical analysis, raised concerns about possible contamination in the calculus DNA, citing his own handling of the specimen in 2021. But the protein evidence, sealed within the bone, stood firm. After years of speculation, the suspense ended here. The Harbin skull is Denisovan. 2 independent molecular signatures, authenticated and published, anchor the story that began in a well in 1933 to a definitive branch of the human family tree. To me, it's astonishing that fragments of Denisovan DNA still shape how millions of us adapt to altitude or resist disease. Even now, as debates over contamination and classification continue, the human story remains unfinished, written in both our genes and the bones we almost lost. What do you think?